Okay, so, when you picture Antarctica, you think of penguins and endless white, right?
Endless white, yeah.
But down at McMurdo Station, there's this intriguing spot
Intriguing spot.
called Building 157,
Okay.
and it's windowless.
Windowless,
And the
yeah.
running joke,
Ooh, I like this already.
that's where they keep the alien bodies.
Aha, of course, right.
It's just that kind of dark humor.
Yeah.
You get in a very isolated place.
Gotcha.
But the real extraterrestrial visitors to Antarctica
Ooh.
are actually scattered all over the ice.
Okay. I'm intrigued. Tell me more.
If you know where to look, we're talking about Antarctic meteorites.
Ah, meteorites.
And today we're going to deep dive into how these visitors from space were first discovered and what they can tell us about the cosmos.
Very cool.
So if you've ever looked up at the night sky and wondered what's out there,
this
one's for you.
Very cool. I love it.
So let's think back to the early 20th century.
Early 20th century. Okay.
Yeah. And all those just incredible polar expeditions.
Yeah.
These were like the space program of their day.
Oh, yeah, totally.
I mean, these wooden ships loaded up with what was then cutting-edge technology.
Yeah, pushing the boundary.
Venturing into totally unmapped territory.
Unmapped territory, yeah.
Fueled by, national ambition.
Right.
And this raw spirit of discovery.
For sure, pushing the limits.
So just like our space missions today push the boundaries of the known.
Yeah.
These early explorers were venturing into the Earth's unknown.
The Earth's unknown, exactly.
Driven by very similar motivations.
Driven by those urges to discover. Yeah.
And one thing that is just fascinating when you consider that era is the sheer audacity of these endeavors.
Audacity, the bravery.
Take Douglas Mawson, for example.
Douglas Mawson, okay.
In 1912, while the race to the South Pole between Scott and Amundsen
the famous race
was capturing the world's attention,
Mawson
launches his own ambitious Australian Antarctic expedition to the Adelie Coast.
Okay, the Adelie Coast. Interesting.
And his aim wasn't the pole itself.
Not the pole.
But a comprehensive exploration and mapping.
Exploration and mapping, okay.
Of that whole region.
Gotcha.
And what's so fascinating is his vision was remarkably modern.
Modern, okay.
For the time.
How so?
He planned to set up a radio station.
A radio station.
For direct communication with Australia.
Direct communication, that's ambitious.
Which was a groundbreaking idea back then.
Groundbreaking, yeah.
He even brought a monoplane.
A monoplane, wow.
For aerial reconnaissance.
For aerial reconnaissance, okay.
Now, sadly, the plane...
Sadly, oh no.
Didn't quite make it off the ground intact.
Didn't make it.
And lost its wings.
Lost its wings out.
In the process.
Okay.
But one of his team members, Frank Bickerton...
Okay.
Proposed converting the wingless fuselage.
The what? The wingless fuselage? Okay.
Into a kind of air tractor on skis.
An air tractor on skis, haha.
To haul sledges.
Haul sledges.
Demonstrating incredible resourcefulness.
Resourcefulness. Yeah, that's impressive for sure. Yeah.
Mawson's overall strategy was to maximize their exploration by dividing his team into smaller sledging parties.
Sledging parties, okay.
Each one tasked with surveying different areas over a single season.
Surveying different areas, I see.
And one of these groups included Mawson himself.
Okay.
Along with Xavier Mertz.
And
Belgrave Ninnis.
All right.
They set out relying on dog teams to pull their sledges.
Dog teams, okay.
And you have to picture the environment here.
Okay, paint me a picture.
This is part of Antarctica that is just notorious. For its relentless hurricane force winds.
Hurricane force, wow.
Average around 80 miles per hour.
80 miles per hour, yikes.
Constantly scouring glaciers that are riddled with these hidden and treacherous crevasses.
Crevasses, so dangerous, yeah.
So unbelievably harsh environment.
Incredibly harsh, yeah.
And tragically,
okay.
After 5 grueling weeks.
5 weeks?
And nearly 300 miles.
300 miles, wow.
Disaster struck.
Oh no.
Mertz happened to glance back.
And
Ninnis had vanished.
Vanished.
They quickly discovered a massive crevasse.
A crevasse, okay.
Concealed by a fragile snow bridge.
A snow bridge?
Oh no. Where Ninnis and his sledge.
Okay.
Carrying the bulk of their vital supplies. Including their food, their tent, even their strongest dogs.
Oh my goodness.
Had fallen into this abyss.
Wow, just a total disaster.
The loss of Ninnis was just a devastating blow.
Devastating, yeah.
Now stranded with minimal food and no shelter.
Minimal food, no shelter.
Mawson and Mertz face a desperate 300-mile trek back to base.
300 miles back.
They were forced to improvise a tent.
Wow.
From their sledge cover and skis.
Sledge cover and skis.
With no other option for sustenance,
Okay.
they began sacrificing their remaining dogs for food.
Oh, gosh, that's awful.
And as you can imagine, their physical condition just deteriorated rapidly.
Deteriorated rapidly, yeah.
They grew incredibly weak.
Yeah.
Suffered from delirium.
Delirium.
Even experienced hallucinations.
Wow.
And tragically, Mertz succumbed to the harsh conditions.
Oh, no.
And died on the return journey.
Died on the return journey.
This left a severely weakened Mawson.
A severely weakened Mawson.
To complete that final agonizing 100 miles alone.
100 miles alone? Wow.
He himself fell into another crevasse.
Oh, my goodness.
But against all odds, managed to pull himself out.
Wow.
When he finally stumbled back to the main base,
oh my God,
he was near the brink of death.
The brink of death.
But here's where the story takes another fascinating turn.
Another turn. Oh, wow. Okay.
Just hours before Mawson's miraculous return,
okay,
his ship had set sail for Australia.
Set sail. Oh, wow.
Leaving behind a small group of individuals
okay.
who hadn't given up hope of his survival.
Hope of his survival, yeah.
Among those waiting was Frank Bickerton.
Frank Bickerton, our air tractor guy.
And while Mawson was slowly recovering from this near-fatal experience,
yeah,
Bickerton had some extraordinary news to share.
Extraordinary news. Oh, my goodness.
You see, while Mawson's party was enduring their ill-fated journey,
okay,
Bickerton had led his own smaller exploratory expedition.
Okay.
His own expedition.
And utilizing that repurposed air tractor.
The air tractor. Oh, no.
Unfortunately, its engine failed relatively early on.
The engine failed? Oh, no.
So Bickerton and his team ended up hauling their sledges by hand.
Hauling by hand?
And across the vast ice.
Oh, wow.
And on December 5th, 1912.
December 5th.
Something truly extraordinary happened.
Extraordinary? Okay. I'm on the edge of my seat.
Amidst this seemingly endless expanse of white,
okay,
Bickerton spotted a small, dark object.
A small, dark object.
Roughly the size of a softball.
Spalltized, okay.
Resting in a shallow depression in the ice.
Okay.
It possessed this distinctive black, shiny, blistered-looking crust. Blistered-looking crust.
Bickerton, sensing its significance, meticulously documented his find.
Okay.
And brought it back for Mawson to examine once he was well enough.
Makes sense.
And Bickerton's description was remarkably accurate.
Accurate, okay.
A rock encased in a dark, scaly exterior.
Okay.
Revealing a crystalline structure within.
Wait, a crystalline structure? All right.
And clearly containing iron.
Iron, interesting.
He even astutely observed that it appeared relatively fresh.
Fresh.
As if it hadn't been exposed on the ice for very long. Once Mawson had regained some strength,
okay,
he confirmed Bickerton's suspicion.
His suspicion? What was it?
This unassuming black rock was, in fact, the very first meteorite.
The very first meteorite
ever discovered in Antarctica.
Incredible.
A remarkable scientific triumph emerging
yeah,
from such profound human tragedy and loss.
Wow, what a story.
But then silence.
Silence.
A very long silence.
A long silence.
It took another 40 years.
40 years?
Before the next Antarctic meteorite was found.
40 years?
This time, by a Russian team on the opposite side of the continent.
On the other side? Wow.
Really underscores just how rare these finds were considered to be at the time.
Wow, that's amazing.
So for decades,
okay,
Antarctic meteorites remained incredibly rare.
Incredibly rare. Okay.
But that all changed dramatically.
Changed dramatically, all right.
With a Japanese expedition in 1969.
1969, okay.
Marking a real turning point in our understanding of these extraterrestrial visitors.
A turning point, okay.
So this brings us to this pivotal moment.
Pivotal moment, all right.
1969.
That's 60.
And the Japanese Antarctic Research Expedition.
Okay.
Making their way to the Yamato Mountains.
The Yamato Mountains.
Now, the leader of this expedition, Masaru Yoshida.
Okay, Masaru Yoshida.
Made a point to visit Professor Masao Garai.
Professor Garai.
Who was a respected figure in Japanese Antarctic geology.
Okay, an expert.
Seeking his blessing for the mission.
Just blessing, okay.
And maybe a request for some geological samples.
Samples, okay.
And Professor Garai, somewhat surprisingly.
Surprisingly, okay.
Wasn't interested in the typical metamorphic rocks.
Not the typical rocks.
That are common in that region.
Okay.
Instead, he specifically asked Yoshida to bring back ultramafic rocks.
Ultramafic rocks, okay.
Or meteorites.
Or meteorites, interesting request.
Now, these are very dense, dark, igneous rocks.
Okay.
Often originating from deep within the Earth or other planetary bodies.
Other planetary bodies, okay.
Imagine the pressure on Yoshida.
Yeah, I bet.
Knowing that only 4 meteorites had been documented in Antarctica up to that point, it must have felt like just an enormous and unlikely request.
For sure.
But as the Japanese team carried out their work, mapping the intricate movements of the ice sheet.
Okay, mapping the ice sheet.
Something entirely unexpected began to occur.
Unexpected, all right.
One of the team members spotted this peculiar, shiny black rock.
Shiny black rock.
Strikingly similar to Bickerton's initial discovery.
Okay, similar to Bickerton's find.
Yoshida collected it.
Okay.
Thinking it might be the kind of specimen Professor Garai was hoping for. But then they found another one.
Another one.
And then another.
And another.
Over the subsequent weeks.
Okay.
Locating these unusual dark rocks.
Dark rocks?
With their glazed surfaces. Became as significant a focus as their original ice mapping mission.
Wow. So it shifted.
By the time they prepared to return to Japan, they'd collected 9.
9? Wow.
Of these enigmatic dark rocks.
9 dark rocks.
With their glassy outer shells.
Interesting.
So Yoshida brings these 9 potential meteorites back.
Okay. 9 potential meteorites.
Undoubtedly anticipating a hero's welcome.
A hero's welcome, yeah.
From Professor Garai.
Professor Garai.
But as fate would have it.
Oh, no, as fate would have it.
The professor was away.
The professor was away.
He left the box containing the rocks.
Okay.
With Professor Garai's wife.
With his wife, okay.
And when Professor Garai finally returned, unaware of the potential significance of the package, he didn't open it right away. It wasn't until Yoshida followed up sometime later that they finally laid the 9 dark stones out on a table. And Professor Garai's initial reaction was, well, let's just say it lacked enthusiasm. He dismissed them as getemano. Which roughly translates to something like oddball items.
Haha.
Or even strange food that most people wouldn't eat.
Strange food. Oh my gosh.
Not exactly the reaction Yoshida had hoped for.
Yeah, not quite the hero's welcome.
After such an unexpected and prolific discovery.
Yeah, 9 meteorites.
But thankfully, Professor Garai, being a true scientist at heart, a true scientist,
decided to take these getemano to his laboratory for closer examination.
Okay, good.
He prepared incredibly thin slices of the rocks. To study them under a microscope. And that's when the significance of the finds really began to emerge.
Okay, the significance emerged. How so?
Each rock displayed that characteristic dark outer rind.
Okay, all rind.
The fusion crust.
Okay.
Formed by the intense heat generated as a meteoroid plunges through the Earth's atmosphere.
The Earth's atmosphere, yeah.
But what's truly fascinating here is what he discovered inside those fusion crusts. The mineral composition, each of the 9 rocks was distinctly different.
Wow.
If they had all been fragments originating from a single meteoroid that broke apart upon entering the atmosphere, they would have exhibited similar mineral composition.
Similar compositions, right. This groundbreaking finding meant something incredible.
Incredible. What was it?
Yoshida's team hadn't stumbled upon a single meteorite fall.
Oh, wow.
But rather the remnants of 9 separate meteorite events.
9 separate events. Incredible.
Which highlights a crucial aspect of scientific discovery.
Yeah, what's that?
Even unexpected or seemingly insignificant finds, when examined with scientific rigor, can lead to major breakthroughs.
Absolutely. That's a great point,
This realization led the Japanese team to a crucial question.
Okay.
Why were so many meteorites concentrated in this one particular area?
Yeah, why there?
Their hypothesis was that the relentless movement of the massive Antarctic ice sheet was acting as a natural conveyor belt.
A conveyor belt, okay.
Accumulating these meteorites over vast timescales and across immense distances.
I see, okay.
And they specifically proposed that the dense ancient blue ice was playing a key role in both preserving the meteorites and concentrating them in specific locations.
Okay, interesting.
And their ideas generated significant excitement and discussion when they presented their findings at the 1973 Meteoritical Society Congress in Davos, Switzerland.
Davos, okay.
Because sitting in the audience that day
All right.
was Bill Cassidy.
Bill Cassidy.
A geologist?
Okay, a geologist.
From the University of Pittsburgh.
From Pittsburgh, okay.
Now, Cassidy had a strong background. In studying meteor impact craters.
And
he even had a prior connection to Douglas Mawson.
Oh, wow, to Mawson.
From his early geological work in Australia.
From Australia, okay.
He wasn't even primarily focused on meteorites at that point.
Interesting.
But the unique environment of Antarctica had always held a particular fascination for him.
Okay.
And that presentation turned out to be a real aha moment for Cassidy.
An aha moment, okay.
As he later described it.
Okay, how did he describe it?
A mental light bulb just went off.
A light bulb went off, haha.
Meteorites are concentrated on the ice in Antarctica. And he immediately grasped the immense potential.
The potential, okay.
While the Apollo missions were costing billions.
Yeah.
To bring back relatively small amounts of lunar rocks.
So not amounts, yeah.
Here was a natural process delivering pieces of the solar system directly to Earth, essentially for free.
For free, wow.
Cassidy quickly developed a comprehensive plan.
A plan, okay.
To systematically survey the Antarctic ice.
Okay, survey the ice.
Collaborating with the insights of the Japanese scientists.
Okay.
To better understand the mechanisms behind this concentration.
Gotcha.
And then to carefully collect a representative collection.
A collection, yeah.
Of these extraterrestrial materials.
I like it.
He diligently applied for funding.
From
the National Science Foundation.
NSF, okay.
But faced initial setbacks.
Oh no.
And rejections. However, he was persistent. And in 1976. His visionary project.
Okay.
The Antarctic Search for Meteorites. Or ANASMET.
Okay.
Was finally established and launched.
Wow, what an accomplishment.
And Cassidy adopted this incredibly forward-thinking.
Okay.
And remarkably generous approach to ANASMET.
Generous, how so?
He recognized the potential for this endeavor to become a competitive gold rush.
Oh, yeah, you can see that.
With different research teams jealously guarding their finds.
Yeah, guarding their finds.
Instead, he instituted an open
okay.
and transparent application process for team members each year.
Okay, an open process.
Fostering collaboration.
Good.
And bringing in new generations of researchers.
Very cool.
Even more importantly.
He
ensured that access to all the recovered meteorites.
Okay, access to the meteorites.
Would be completely free.
Free? Wow.
And readily available to scientists worldwide. With the explicit goal of maximizing scientific discovery.
Okay.
And knowledge sharing.
Very good.
As Professor Ralph Harvey.
Okay.
The current principal investigator for ANASMET.
The PI.
Eloquently stated.
Okay, how did he put it?
This is planetary exploration done cheap and crowdsourced.
I love it.
In my humble opinion, there's never been a boon to science that compares.
What a great quote. Yeah, I completely agree.
And it's difficult to argue with that assessment.
It really is.
Since its inception in 1976.
Okay.
ANASMET has operated continuously. And has been responsible for the recovery of an astounding number of meteorites.
An astounding number? How many are we talking?
Over 50,000 by the most recent count.
Over 50,000. Wow.
It's absolutely incredible.
They're incredible, yeah.
Now, for someone like you, who's likely been down to McMurdo, and experienced the sheer scale of that Antarctic ice.
The scale of it is just, it's hard to comprehend.
And for someone like me, who's always just been curious, why is this blue ice?
Why blue ice?
So particularly conducive.
Okay.
To finding meteorites.
That is the question, isn't it? Yeah.
I mean, this mechanism reveals that Antarctica isn't just a blank canvas.
Right, not just a blank canvas.
It's actively curating a collection of extraterrestrial material. Offering us a biased,
okay,
but incredibly rich sample of what's out there.
It is a rich sample, yeah.
So why is that?
So that's a great question.
Yeah.
Well, meteorites fall across the entire globe.
Okay, across the globe.
At roughly the same rate.
Same rate, okay.
The critical difference in Antarctica is that they land on a massive dynamic ice sheet.
A dynamic ice sheet.
Right. And as Bill Cassidy demonstrated through his early, rather informal rock races.
Rock races. Haha.
Literally marking rocks placed on the ice.
Okay, marking rocks.
And meticulously tracking their movement over successive years.
Okay, tracking their movement.
This ice is in a constant state of motion.
Constant motion.
Although the speed of this movement can vary significantly depending on the specific location.
Right, so these meteorites aren't just staying where they initially land.
Right.
They're not staying put. They're being carried along.
Carried along.
By the immense power of the moving ice.
The moving ice, yeah.
Exactly.
So when a meteorite lands on the Antarctic ice...
Okay, lands on the ice.
It inevitably gets buried by subsequent snowfall.
Buried by snow.
And in the incredibly cold and arid interior of the continent, this accumulated snow gradually compacts under its own weight, transforming into dense glacial ice.
Dense glacial ice.
Sometimes forming the distinctive blue ice.
Blue ice.
Which represents the oldest.
The oldest, okay.
And most compressed layers of the ice sheet.
Of the ice sheet, okay.
This vast expanse of ice then flows.
Okay.
Albeit slowly in many areas.
Slowly, yeah.
Inexorably towards the coast.
Towards the coast.
Effectively entombing. And transporting the meteorites within it.
Okay, so it's carrying them along.
Carrying them along.
And the majority of this ice, along with its rocky passengers, eventually calves off into the ocean.
Into the ocean as icebergs.
As icebergs, yeah.
Which would mean those meteorites are lost to science forever.
Lost forever.
So what prevents this from happening to all of them?
That is a great question. The crucial factor is the underlying land mass.
Okay, the land mass.
Beneath the ice sheet.
Beneath the ice sheet.
In regions where subglacial mountains. There are other significant geological
obstructions
impede the otherwise smooth flow of the ice.
Okay, impede the flow. The immense ice sheet effectively backs up.
It backs up. Okay.
Think of it like that conveyor belt analogy we used earlier.
Okay, you can figure it out.
When the belt encounters a wall.
Yeah, hits a wall.
Everything on it starts to pile up.
Starts to pile up, right.
In these zones of obstruction.
Okay.
The deeper, older layers of ice.
Okay, the deeper layers.
The blue ice.
The blue ice.
Are forced upward.
Forced upward.
As upwards.
And extruded to the surface.
To the surface. Yeah. Essentially bringing the trapped meteorites with them.
Bringing the meteorites.
And concentrating them.
Concentrating them.
At the base or on the upwind side of these physical barriers.
Okay, I see.
So that elegant equation.
The equation.
That the Japanese team and Bill Cassidy essentially deciphered.
Yeah, they deciphered it.
The continuous movement of the ice sheet.
Ice sheet movement?
Combined with the presence of geological barriers. Creates prime locations, potential meteorite finds.
Potential meteorite finds, exactly.
Yeah.
So we now understand how Antarctica has become this incredible repository of extraterrestrial rocks.
This repository, yeah.
But what exactly can these space rocks tell us?
That's the next question, isn't it?
You mentioned earlier that some of the atoms within them.
The atoms, right?
Hold clues to their ancient history.
Clues to their history, for sure.
Absolutely.
One particularly powerful tool for unraveling their past is aluminum-26 dating.
Aluminum-26 dating.
When these rocks are orbiting in the vacuum of space.
Okay.
As part of asteroids or other celestial bodies.
Yeah.
They are constantly bombarded by high-energy cosmic rays.
Cosmic rays, okay.
This intense radiation interacts with the elements within the rock.
Okay.
Transforming some atoms into aluminum-26.
Transforming them into aluminum-26.
Now, aluminum-26 is a radioactive isotope.
Okay, a radioactive isotope.
And once the meteorite lands on Earth. Our planet's atmosphere and magnetic field.
Yeah, our atmosphere.
Will provide a significant shield.
A shield, okay.
Reducing further cosmic ray bombardment.
Reducing the bombardment.
Okay. As a result.
Okay, as a result.
The production of new aluminum-26 essentially ceases. And the existing aluminum-26 begins to decay. At a predictable rate.
So a meteorite that has been on Earth for a relative